in my graph and continually getting a shorter edges in my graph and continually getting a shorter path, right? So if the minimum weight of a path from S to T actually goes through an infinite number of edges, then this isn't really well defined, right? So I'm going to change this minimum here to, in mathematics, just to be specific, we call it an infimum, right? So if, in the case where the weight of a shortest path can approach arbitrarily small, right, then we'll call this thing minus infinity, okay? So when does that occur? When does that occur? When could we have our shortest path go through lots and lots of vertices? Well, let's actually take a look at this example here. Can someone tell me what the shortest path is from A to actually any vertex in this graph? Ah, okay. So, well, we could look at this path I have to B. Let's just take a look at B, right? I have a path going from A to B that is -5. Okay, that's pretty good. That's pretty small, right? And it seems that if I go around this graph through another way, it might be bigger, right? So I go at 7 plus 3 plus 8, that's 15, minus 1, that's 14. That's much bigger than my -5. So it seems like -5 should be good, right? Anyone have a problem with this path? Or a problem with this being the shortest path? And what your colleague just informed me was that there's something interesting happening here in this graph. In particular, we have a cycle from B to F to G to C that has negative total weight, right? Back to B, right? This has -4 plus 2 plus 1 minus 1, right? So that total cycle has a cycle weight of -2, right? This is a negative weight cycle. So if I wanted to get to B, I could go there via this -5 weight edge. But every time I circled around this cycle, I incur -2 to my path weight, right? So I just keep going around this cycle over and over and over and over and over and over again, and I don't have any finite length minimum weight path, right? In such cases, we just say that delta is -infinity, right? So the problem here is that we could have negative weight cycles. Deserves a capital letter. Negative weight cycles. It's a problem. Okay? In particular, if there exists a path from S to some vertex V that goes through a vertex on a negative weight cycle, then I can take that path to that vertex, circle around the negative weight cycle, and then proceed to V, and I can take that cycle as many times as I want. Then this delta SV, we're going to set to -infinity, okay? And in such cases, in our shortest paths algorithm, we don't really care about what the shortest path is, right? We're not even going to deal with parent pointers here, right? Because there is no finite length shortest path. So I'm just going to kind of throw up my hands in the air and say, you know what, I can't return you a shortest path. but I might want to return to you a negative weight cycle, right? If you told me that this thing has bad weight, right, maybe I want you to tell me what a path is that goes through a negative weight cycle to get back to S, right? So that's what we're going to talk about next lecture. This lecture, we are not going to talk about that. We are going to talk about weighted shortest paths, though. That's what the remainder of this this unit on graphs is really about, is weighted shortest paths. Okay, so in weighted shortest paths, we actually know an algorithm already to solve a subset of weighted shortest paths, namely BFS, right? Now, you're like, wait, Jason, BFS doesn't solve weighted shortest paths. We didn't even know about weighted graphs then, right? How does that solve weighted shortest paths? Well, there's a couple cases where we might be able to reduce to solving shortest paths using BFS. Can anyone think of such a scenario? So let's say, I mean, kind of what we did before was we counted the number of edges, right? So if we gave a weight of 1 to every edge in my graph, then just that graph, that weighted graph, corresponds to an unweighted graph using the other distance metric, right? So in that case, BFS just solves our problem. And in fact, we can generalize further. What if all of our weights were positive, but the same value, right? If it was all positive and the same value, then we could just divide by that value, right? Now we have an unweighted graph, which we can run BFS, and then multiply shortest path distances by that value later on. And in fact, there's one further generalization we could make, which is a little bit of a tricky graph transformation problem. But we can also get this linear time algorithm for weighted single source shortest paths in contexts where the weights aren't that large, okay? So if I have positive edge weights, right? If I have a positive edge weight that's, say, using my weight color here, that's like weight of 4, right? That's kind of problematic because I don't know how to simulate that using an unweighted graph, or do I? Anyone have an idea of how I could simulate an edge of weight 4 with an unweighted graph? Yeah.
Have 4 edges of weight 1.
Yeah, I can just put 4 edges of weight 1 in parallel here. In series, okay. The opposite of parallel. Okay, I can just convert this here into 1, 2, 3, 4 edges. And if I do that for every edge in my graph and we have positive edge weights, then that transformation can hold. Now, that's not necessarily a good transformation to make. Why?
The weight might be very big.
Yeah, the weights might be very big compared to the number of vertices and edges in my graph. However, if the sum of all weights in my graph is asymptotically less than V plus E, right, we can get a linear time algorithm again by reducing to BFS. Okay, so that's great. Today, but in general, that gives us a linear time algorithm in these very special cases. And in general, it's an open problem. We don't know whether we can solve the single source shortest paths problem in the weighted context for general graphs in linear time. We don't know how to do it, right? But what we do know are some algorithms that do pretty well, and that's what we use all the time.